Okay, we're going to continue our discussion about energy and states of matter, and we're going to start going into a little bit more detail about how compounds or substances change their state. And when we say the state of something, we mean whether it's a solid, a liquid, or a gas. So first we're going to talk about this on a conceptual level, and then we're going to do some calculations to calculate the energy to go through these phase changes. The first thing we want to talk about then is the structure of a solid, a liquid, and a gas. So what we'll talk about first is how fast the atoms are moving and what type of shape they take in a container. So first we'll talk about how fast the atoms are moving, and then we'll talk about the shape and compressibility of the substances that they form. So first of all, let's start with the solid. As you can see, and as I'm sure you probably already have some sort of conceptual idea, as you can see, the atoms in a solid are packed closely together. They move very slightly by vibrating back and forth. They have a definite shape, and they have a definite volume. The compressibility of a solid is also minimal. Liquids, on the other hand, these atoms are able to flow around one another. And when we talk a little bit more about the bonding involved, what we'll talk about are the intermolecular forces that keep these atoms from flying apart from one another. So in a liquid, the atoms flow around one another. In a liquid, the substance takes the shape of its container, and also the compressibility of a liquid is very low. A gas, on the other hand, the atoms are flying past one another. In other words, there's lots of space in between the atoms. The gas takes the shape of whatever container it's holding, and gases are highly compressible. So if you think back to our podcast about kinetic energy, the one with the highest kinetic energy would be the gas. The one with the lowest kinetic energy would be the solid, assuming you're talking about the same compound. Okay, what we're going to talk about is how something goes from a liquid to a gas. And to understand that, we need to talk a little bit about vapor pressure. Basically, vapor pressure can be described as the pressure above a certain liquid in a closed system. So for example, let's say you have a beaker, and the top of that beaker is sealed, and in that beaker you have a liquid. Let's just say it's water. You have molecules in the liquid phase here, and what happens is some of those molecules have a little bit more energy than other molecules, and they will leave the liquid phase and go into the vapor phase. It's those molecules on the surface that are going to do that. One way you can think about this is think about water molecules. Whoops. Let me try that again. Water molecules on the surface, and then water molecules below the surface. If you remember our talk about hydrogen bonding, there's hydrogen bonding going on in between these molecules below the surface. So the molecules below the surface are going to have lots of other water molecules holding onto it, essentially, with this hydrogen bonding. The molecules on the surface only have things below them, or molecules below them, holding them down with hydrogen bonding. So they have a little bit easier time leaving the liquid phase and going into the gas phase. The primary reason, though, that we have vapor above a liquid is explained using this diagram. What this diagram is a probability distribution. And when you take your calculus course, what you're going to talk about is that the space underneath the curve represents 100% of the molecules. Our x-axis here represents kinetic energy, so essentially it's temperature. So if we have a system here at one temperature, let's just assume the temperature is 75 degrees Celsius of this system. What this means is that the majority of the molecules are going to have roughly the same kinetic energy or the same temperature. However, you have a small percentage of molecules that are going to have higher kinetic energy. And you'll have some molecules that even have a lower percent or lower kinetic energy. So it's these molecules in the system, let's say that's 5%, that are going to have more energy than the rest of the system. Those molecules are going to be the ones that are capable of leaving the liquid phase and going into the vapor phase. So if we look at our next diagram, all we're doing here is increasing the temperature. So if you think of it on a conceptual level, if you increase the temperature of that water to 90 degrees Celsius, you're flattening this curve out, which is making the percentage or the number of molecules that are going to have enough energy to leave that liquid phase even higher. So as you turn up the temperature, more of those water molecules will leave the liquid phase and go into the vapor phase. That's why in the summertime, when you hang clothes out on the clothesline, they'll dry a lot quicker than they would in the spring or fall, and certainly quicker than the winter time. So in our beaker of water here, like we said, we have those water molecules in the liquid phase. A few of them have enough energy, and the ones on the surface have less hydrogen bonding, are going up into the gas phase. It's that pressure that those gas molecules exert on the sides of the container is what we refer to as vapor pressure. Now when we say the word vapor, a vapor is nothing more than a gas of some substance that's normally a liquid at room temperature. In other words, water is normally a liquid at room temperature, so if we have water in the gaseous phase, we call it water vapor. Oxygen, for example, is normally in the gas phase, so we don't call it oxygen vapor, we call it oxygen gas. Okay, so then what does vapor pressure have to do with a substance going from the liquid phase to the gas phase? Well, the definition of boiling point is when the vapor pressure of a liquid equals the atmospheric pressure. So if you think about our beaker here again, you've got atmospheric pressure pushing down on the surface, holding those, or quite literally pushing on those water molecules, keeping them in the liquid phase. And let's say our atmospheric pressure here is 1 atmosphere. If we increase the temperature of this system until the vapor pressure were to equal 1 atmosphere, what would happen is the substance would start to boil. You would have those vapor bubbles forming in the solution. Those vapor bubbles go to the surface, pop out of the surface, and it's what we recognize as boiling water. So you might think, well, if the system is open, how can we have a vapor pressure? Well, if you were to close this system, measure that vapor pressure at 100 degrees Celsius for water, what you would have is a vapor pressure of 1 atmosphere. So when a substance's vapor pressure is equal to whatever atmospheric pressure pushing down on it, the substance will start to boil. So if you go up to a mountain, let's say you live in Boulder, Colorado, and you start cooking spaghetti, since air pressure is less at higher altitude, water will boil at a lower temperature. In other words, you only have to heat up the liquid water to approximately 95 degrees Celsius to have its vapor pressure equal the lower atmospheric pressure. So what you can see in this diagram here, don't worry about this one, what you can see in this diagram is how vapor pressures increase with increasing temperature. So if you were to look at water, for example, as you increase the temperature, the vapor pressure rises and rises until you reach its particular boiling point. You can see different substances have higher vapor pressures, so they're going to boil at lower temperatures. So in other words, ethanol will have a boiling point of 78.4 degrees Celsius. So as a review then, as you add energy to a system, or as you increase the temperature of a system, the molecules in that system are simply going to move faster and faster to go from the solid phase to the liquid phase to the gas phase. Remember, what happens in a compound, or let's say a substance, what keeps it in a certain state, in other words, the solid state, are the interactions in between the different atoms that are next to one another and the kinetic energy in the system. So if you increase that kinetic energy and get those molecules moving faster and faster, what will happen is that they'll start to break those intermolecular forces and go from a rigid structure to a flowing structure to a gaseous structure. So as you increase kinetic energy, you increase the speed of those molecules, you start to break apart those intermolecular forces, and those atoms leave the system and change state. So what we want to take a look at here is what we call a phase diagram. And what this does is graphically show you how something goes from the solid phase to the liquid phase to the gas phase as you increase the temperature at certain pressures. So as we said before, atmospheric pressure, normal atmospheric pressure, is 1 atmosphere. So with this graph here, if you're looking at this, if we were right here, that would be a pretty cold temperature. In other words, it's below 0 degrees Celsius. So we're in the solid phase. So as you increase the temperature, the temperature of that ice gets higher and higher until it reaches 0 degrees Celsius. It goes through a phase change. Increase the temperature to greater than 0 degrees Celsius, you go into the liquid phase. Keep increasing the temperature until you reach 100 degrees Celsius, and then you go into the gaseous phase. So what this implies is if you had a low pressure, something down here, I'm not sure what that pressure would be, let's just say it's 0.1 atmospheres. As you increase the temperature and increase the temperature, you go straight from the solid phase right into the gas phase. You wouldn't go through the liquid phase. So when you go straight from solid to gas, we call that sublimation. When you go the opposite, gas to solid, we call that deposition. Okay, a few points on this graph that we want to point out. We have the triple point, which is that point right there. The triple point is the point where the solid, liquid, and gas phases at a certain pressure will all exist at a certain temperature. So at that temperature and pressure, solid, liquid, and gas exist in the same system. The other point we want to point out is the critical point, oftentimes called the critical temperature. And what that is the temperature at which a substance, no matter how you change the pressure, will always be in the gaseous phase. And if you think about that, that should make sense. If you increase the temperature to a point where no matter how much pressure you're putting on those molecules, they're going to overcome those intermolecular forces, then the compound will stay in the gaseous phase. What we have here is just another phase diagram, but this one happens to be for carbon dioxide. As you can see with carbon dioxide, you go from the solid phase right into the gas phase at normal atmospheric pressure. In other words, to get liquid carbon dioxide, you have to increase the pressure of the system substantially. Oftentimes at this point in a lecture, a student will ask the question, well then what's the difference between boil and evaporation? In other words, how can you have something evaporate at room temperature when to go through a phase change with water you have to get it to 100 degrees Celsius? Well, in evaporation, if you think back to our probability distribution, in evaporation at a certain temperature you've got those molecules that have enough energy to leave the system. If you increase the temperature to the boiling point, what happens is you flatten out that graph, so you push all of the molecules past that point, in other words the boiling point, so all of the molecules will go through that phase change. So evaporation, it's just the number of molecules at the top of that graph that are going to make it through the phase change. Boiling is when you force all of the molecules through. Okay, that's it for this podcast. It's a very brief and general description of phase changes. Go through it once or twice if you need to. There are some important concepts that we just discussed.